Okay, it's time. So let's start. So the second speaker is Professor Antonio Ray. He will give the last talk on the Euler systems and Beilinson-Flach elements. So please start.
Thank you for the introduction. So let me just share my screen. Okay. So last time I finished with one application of this Beilinson Kato element where you can build up an Euler system which allows you to prove one inclusion of the main conjecture, namely the p-adic L function of an elliptic curve at an ordinary prime p will be included in the characteristic idea of the punchy eigendual of the summer group. So today I want to tell you roughly how this Euler system is constructed without going into the technical details. Again, the idea is really to give you a rough idea how it works, rather than telling you exactly all the difficult steps that you have to do. So, so let me begin by fixing a level n. So n will be at least 3, an integer, and I'll write yn to be the modular curve parameterizing elliptic curves with a basis E1 and E2. Here, E1 and E2 is a basis of the n torsion of E, and we will also fix C, an integer, which is co-prime to 6 times n. Once you have fixed this, so you have the following Siegel units. So for all alpha and beta, which are in 1 over nz mod z, and I want them to be not both 0. Given alpha and beta and all these choices we have made, we have what we call a Siegel unit, which is a function on the modular curve. So we'll denote it by CG alpha beta. And it will be a unit on this curve, and this is why we call it the Siegel unit. So, and it has a nice norm relation, which which is given by this. So C G alpha beta will be equal to product of CG alpha prime beta prime, where alpha prime and beta prime will be elements in Q mod Z, such that M alpha prime is alpha and M beta prime is beta. So so a product of these different Siegel units give you another Siegel unit, and so so as you can imagine, this kind of non-relation resembles a little bit what we are looking for in an Euler system. So you can imagine these units are useful for constructing an Euler system. So in order to tell you more explicitly how construction goes, so I want to introduce another modular curve. So let yn be the modular curve parameterizing E1, E2. So now E1 will be a base, an element in EM, and E2 will be an element in the n torsion. And so for an integer L, M and N, such that M divide L and N divide L, then we have this natural projection map going from YL to YMN, right? And so so for C, which is co-prime to 6M and 6N, sorry. Then we can define the following elements, which I will write as C, D, Z, M, N, which is given by I write it as a Manning symbol in the K2 of the modular curve. So remember, the K2 of a curve is given by something like this, right? So you want to have the tensor product of the unit quotient out by this relation, and so yeah, and so here because I have two units on the curve, so that gives me an element in the K2 of this curve, and this element in K2 will satisfy a norm relation thanks to the norm relation that I told you about. So when you look at, let's say, the norm map going from K2 of YMLNL to KLYMN, you will sense the element that I just defined. So I have elements at this level. You will send this to the element downstairs if L divides M and L divides N. Otherwise, I will have some Euler factor in the Hecker operators. So I won't specify the exact relation, but you would be given by some Euler factor involving the Hecker operator at L. Otherwise, so well, like I said, I'm not giving you the precise detail of the Euler factor because there are different cases to consider and it's kind of complicated to write out. But the point is that it resembles a lot of what we are looking for in an Euler system. Okay, so remember when I told you about cyclotomic units, how we can think of the cyclotomic units as the H1 of ZP1 via some Kuma map, essentially. And so the way we do it for modular curve is kind of similar. So so you have this connecting map. So we have so you can go from, if I give you so here, let's say Y. Okay, sorry. So let me move this. Just for simplicity, let me, oh, no, that's not what I want. Okay. So let Y to be YMN for the time being. So you have a map, let's call this H, going from OY cross to H1Y ZPN1. So here, this is Ital cohomology. When I write it like this, without saying anything, it's the Ital cohomology on the curve. And so yeah, so you have a bit like the Kuma map you have seen for Galois cohomology. Here we have a map like this, and then you have a map going from K2 of Y to given like this. So it would be H2 of Y the Pn2, and then I give you a many symbol. I can just look at the curve product of HF and HG, right? And so that gives me a system of elements. I would call this CD is a MPN, NPN into the H2 of YMPN, NPN is a PN2. Okay, so these elements satisfy some nice norm relation. So as you allow n to vary, it gives you a system of elements that will be inside some inverse system. And so that would allow me to get something like this. So here I have to apply some spectral sequence and some regulator maps going from the Italic cohomology to the Galois cohomology. And so I won't, maybe I'll just skip the details, but I want to say that, here I also need to use another observation, which is that when I have a curve on YMN, I can send this to Y1N tensor Q zeta M. So together with all this, we get something like this. So we get elements in, well, maybe I'll use another symbol. Let's call this curly Z. It will be in Z M P N inside H1 Q adjoin MPN, and then I will. So this is the Galois cohomology acting on some Italic cohomology. So, and once you have these elements, which again will satisfy a norm relation thanks to proposition 2.2, then you see you are not very far from getting an Euler system. And in fact, remember we are interested in defining an Euler system for an elliptic curve. In fact, here we can do it for a modular form of level f. This is because if f is a way to modular form, then the representation, I mean, here I'm talking about eigencast form of level n. So that's eigencast form. Then we have a representation associated to the modular form, and the modular form, the representation is a quotient of this Italic cohomology. And so you can then look at the image of this element as you look at when you look at the quotient, like the fact that TF is a quotient of this, you have a natural map going from H1Q zeta MPN H1 tau Y1N Q bar ZP1 to H1 Q zeta MPN TF. And so these elements give me an element in this Galois cohomology. So maybe I'll. So maybe I'll call this as F and Pn, yes, which will be, sorry, being here, and then the fact that these elements are construct using these single units which satisfy this norm relation by proposition 2.2 tells me that these elements will satisfy the norm relation that you desire, and it gives you an Euler system. So remember when I talked about cyclotomic units, I told you that one main condition is the norm relation, but the other condition is that you want your elements to encode some kind of arithmetic information. Otherwise, it's not a very meaningful Euler system. So in this case, you can show that this Euler system will be related to L values of F. So these elements twisted by some Dirichlet characters, depending on the level, right? So because here, your M and Pn might change, so you would be twisting by different Dirichlet characters of different conductor, and this is how you can show that this element will give you the p-adic L function that I told you last time. So I told you that the Beilinson-Kato element will be sent to the p-adic L function of the elliptic curve. So in general, it works for any modular form. And so this is because we can find this link between these elements to L values of F. Yeah, sorry, didn't say F here. Of F. Yeah. So here I just told you what happens for the weight
I have
modular
one question. So
yes.
What is the relation between like CD capital Z and this small z MPN?
Yeah, so so I guess here I have this auxiliary choice of C and D, and that's a way to get rid of the dependence of C and D. So you can show that when you change C and D, they differ by some fixed factor, and then you can get rid of that factor under some appropriate conditions. So I'm not going into the details of how to get rid of this constant. So
thank you.
Yeah. So so here I only talked about weight 2K. So for higher weight modular form, you can do something similar, but instead of looking at this eta cohomology, you have to look at some more complicated sheaf on the modular curve. So I won't go into the details of that. So okay, so here, sorry. So now I want to move on to the last section of my talks, which is about Beilinson-Flach elements. So references for this section will be the first paper that I recommend is the paper by Flack, which is titled A Finiteness Theorem for the Symmetric Square of an elliptic curve. Another paper that you can have a look is a paper of mine with Loeffler and Zabis called Euler Systems for Ranking Hilbert Convolutions of Modular modular bounds.
Sorry, Antonio, for the previous section, you said the reference is the paper of Kato, or some other reference also you'd like to give?
Yeah, so I think for this section, it's only Kato's paper.
Okay.
Yeah, I think I didn't mention other papers in this section. Yeah, this section is only Kato paper. Like everything I said in chapter 3, you can find in Kato's paper with much more details and much better explanation than what I have just said. So,
okay, yeah, thanks.
Okay, so I want to begin by telling you what Flack did. So Flack, if you look at this paper, he was interested. Sorry, still early for me. He was interested in studying the summer group of the symmetric square representation of the Tate module of an elliptic curve. So here E is an elliptic curve with good reduction at P. Okay. So in other words, if you look at tensor product of the Tate module with itself, it decomposes into symmetric square and the alternating power. So this will be of rank 3, and this will be of rank 1. And to study this representation, he constructs his classes. He constructs classes which I would denote by CL. It will be elements in H1QT where L is indexed by some set of primes, which is not P, not the infinite prime, nor the bad prime. So is indexed. Okay, and then he used Colli-Fagan's method for using this set of classes to give some finite result on the summer group of the symmetric square. So how does he construct these elements? So as you can see here, this is not quite an Euler system because for an Euler system, you need more elements than that. You need to have some square-free integers multiplied by some power of P. So here, this is not quite an Euler system, but this is still a very useful set of elements to work with. So he used the Gersten complex. So I'll tell you what it is. So given a variety X, which is, let's say, smooth and of finite type over some field K, then we have the following. So I'll write this complex as G to X. So I'll just write this down and then I'll tell you what they are. So sorry about my K. So I have big K and small K. So I hope you see the difference. And also I have small X and big X. So I hope they are clear which one is small, which one is big. Okay, so the complex is like this. And here xi is this set of points of codimension I. Okay, so right, so kx is just the so this small k, right? Small k, small x is just the function field at x, and then here x0, x1, x2 is this set of points of codimension I in x. And so I have the k2 of this function field, and then here I have just the function field, and I look at the non-zero element in this field, and then going from these functions, I have some divisor function, and then that give me this disjoint unions indexed by x2. So why is this complex interesting? It is because we have a theorem which tells me that when you look at the first cohomology of this complex, you will get the child group of this variety. And so why is it a good thing? It is because elements in this child group can be sent to the Hida cohomology of X like this via a certain regulator map, which I won't go into. Okay, and so so it's a bit similar to what we have seen in the construction for the Beilinson-Kato element, right? So once you have something in Hida cohomology, then you can go to Galois cohomology. So indeed, what Flack considered was when the case X is the product of your elliptic curve itself, then we get a map going from this Hida cohomology to the Galois cohomology of this. And then you can then further send this to an element in H1Q of T. So in other words, in order to construct his classes CL, then it is enough to find elements in H1G2X. So
when you write the disjoint union, do you mean something like the direct sum of those abelian groups?
I just mean the direct product. So I can have interlinkment. So when you write when you write a direct sum, usually you want to have only finitely many. So here I can have I just take the like the direct product.
Okay.
So to construct CL, we construct an element in this H1G2X. And so by the description of my complex, it is equivalent to saying it is enough. Well, maybe I'll just say, so yeah, maybe I'll just say, so we construct some CI, no, sorry, not L, sorry, C and phi, where C will be in X1 and phi is an element in KC cross. So in other words, I want to find some subvariety which is of codimension 1, and on this subvariety I want to define a function, and I want to make sure that the divisor of phi is 0. And so how do we find this subvariety? So here my variety is of dimension 2, right? I'm looking at the product of two elliptic curves. So in other words, I need to find something which is of dimension 1. So the way Flack did it was to consider this map. So I'll write this as pi times pi WL. So let me write this down. So here, pi is just the natural projection map. And WL is the Eichen-Langmuir. And so, yeah, so here it's a bit, well, I mean, yeah, you start with something which is of dimension 1, and then it's almost like a diagonal embedding, except you twist the second factor by the Eichen-Langmuir. And so the image will still be dimension 1. So you do get codimension 1 subvariety here. So you write ZLN for the image. So this is the first part. You first of all have to find this element in X1. So this is what he used. And then to define a function, so he considered the following. So it will give you it will give you indeed like, so here what is didn't say what is, where G is a modular form of weight K and level N, and so this will give you an element which is which will be a function on this curve, which turns out to be a unit. You can work out the divisor of this function quite explicitly. You can find out where the pole and zeros are, and so in Flack's construction. So he used this. So what modular form? So here I have to choose a modular form, right? So this G is just any modular form. So Flack constructs an element in this H1 G2X using this. So using this subvariety with the function given by the delta function. So delta is a discriminant function. So it's the weight 12 modular form. So this is what Flack did in order to construct his elements, and then he used this to study the representation coming from the symmetric square. And so now I want to move on to what we call the Beilinson-Flach elements, which is somehow inspired by the two constructions you have seen, like the Beilinson-Kato element and the element of Flack. So Beilinson-Flach element combine the Siegel units used in the Beilinson-Kato elements with the method of Flack. So here we are not just looking at symmetric square. We are looking at tensor product of the representations coming from two modular forms. But the idea is pretty similar. So here I will be looking at the modular curve. So let's say I call this, consider a map like this, EMN. And I look at this map, presenting Z to Z and Z plus 1 over M. And again, this is a variety of dimension 1. So now this map would give me a subvariety of codimension 1. And so I will write CMN for the image of this map. And similar to what Flack did, I look at this variety, I look at a function on this subvariety. And the function that I use will be the Siegel units that I discussed earlier in the earlier construction of Beilinson-Kato elements. And so just as what Flack did, this via the Gersten complex give me an element in some Nitaka homology. So all right, so this gives an element. Let's call this ZMN. Right, and then via some via some regulator map, you have something in the child group, and then you can send this element to something in the Galois homology. So via certain regulator maps, we then get an element in here. So it will be H1Q zeta M, H1 Y1 bar, P, sorry, maybe. Like this. And then if I have two modular forms, F and G, that are of weight 2 and level n, a bit like what we did earlier with the construction in Beilinson-Kato elements, I can find a map going from this Galois cohomology on DC tau cohomology to TF tensor with TG, where F and G are modular forms of weight 2 and level n. Okay, so like the construction, as you can see, really is inspired by what Flack did for the symmetric square case. And so, except that here we are trying to define an Euler system, so we need to do a little bit more work than just constructing these elements. Like we want to know what kind of norm relation we get. And it turns out to be a little bit more complicated than the earlier cases. So here, I want to explain to you what kind of norm relation we get. So, so I will go back to discussing what kind of norm relation these elements satisfy. So let me describe them to you now. So I describe the norm relation when L divides N and L divides M. So this is the simplest one. Yeah. Leave it like that. right, so this tau L is some degeneracy map between these two modular curves. So as yeah, so it is essentially given by Z sent to Z over L, and then so this is when I realized this map on the upper half plane. So now I look at the product of these two maps induced on this group. So you will send these elements, which I have written down here. You will send this map to send this element to UL prime acted on the element downstairs. Sorry, this should be an N. Okay, so what is this UL prime? So let me describe this. Yeah, so so this ym brackets ln is in some way in between ymn and ymln, in the sense that it parameterizes elliptic curves with basis element in em, a basis element in en, and also a cyclic subgroup of all the ml inside E. Okay, and so so my UL prime is defined by these two projection map given by Z sent to Z and Z sent to Z over L, and so so it is essentially some kind of dual of the Heck operator at L, if you want. So so in other words, what happens is that when you once you know that you have this relation, right? So this relation is not like the usual norm relation that we want. The usual norm relation would just send, when L divides M and N, you want your element to send to the element downstairs. So what happens is that if you have if you define your elements, like I said earlier here, where did I? Sorry, I didn't give it a name, right? So maybe, okay, so maybe I call this element ZMFG. Okay, so here, what I will actually get is that we will get if alpha f, and so maybe I'll write it like this. So here, when I define my elements like this earlier, assuming L divides N, and we have UL prime F equals to alpha LF and UL prime G equals to alpha LG, then you would get something like this. You will get the norm relation you would get is this. So it is not quite the usual norm relation you would like for an Euler system because of this extra factor. So somehow you will need to massage this element if you want to turn this into an Euler system. So what you need to do is to do the following. So we define EF, FG, Pn to be 1 over alpha F, alpha G, and Z, M, P, and FG. So once you have modified your element like this, then you will get the right relation that you want. And so so the problem is that here I'm destroying the inequality unless alpha F and alpha G are periodic union. So what happens is this. So you actually have to consider the ordinary case and the non-ordinary case separately. So in fact, okay. So now let's say I have F0 and G0. Yeah, sorry. So I guess I'm saying, yeah, I'm being a bit sloppy here. So I guess, yeah, my L here, my L is now P. So okay, so given, okay, so let's say given two modular forms, F, yeah, maybe, yeah, sorry, maybe I shouldn't, yeah, maybe I shouldn't introduce this new notation to confuse you further. Yeah, so maybe I'll just say this. So let's say, yeah, if F and G are ordinary at P, then we do get an Euler system after you have modified these elements by this alpha F and alpha G. And then I just want to say that these elements do have some arithmetic information in the sense that they are related to some L values. So so this is proved by Bertolini, Darmon, and Roger. So they show that these elements do encode some arithmetic information. These elements are related to L function of the Rankin-Selberg product of F and G, meaning is the L function given by like this. Okay, and then once you have all this information, you can do something similar to the earlier cases where you can prove okay. Can prove one inclusion of the Iwasawa main conjecture, which relates the summer group defined using Greenberg's condition. And so okay, on the algebraic side, you have the you have some Selma group where the local condition is given by Greenberg's local condition. And then on the analytic side, we will have the Hida PLL function. Okay. Another thing that I want to tell you is that here I only told you what happened at the weight 2 case, but you can do something similar for higher weight modular form as well, and you can even deform these elements in Hida family. So I'll just state this. So we can also define these elements for higher weights modular forms, and even deform them in Hida families. So these are works by King's Lovelace service. So in fact, you have now 3 variables going on, and then you can talk about a 3-variable main conjecture. And so a work of Bujuk and Ochi use these elements to prove a 3-variable one inclusion of the Iwasawa main conjecture. Okay. And then you can also do something similar to what Flack did, in the sense that you can take F equals to G, and then you get the tensor product of TF with TG, and then inside you have the symmetric square. So you can also do something with the symmetric square. So when F is equal to G, we can go back to the setting of Flack and study the Iwasawa main conjecture for the symmetric square representation associated to TF. There are some technicalities. You have to twist it by some Dirichlet character to make sure things work, but I won't go into the details of that. So, but this is work of Lovelace service. Okay. Now, for the remaining 7 minutes of my lecture, I want to say something about the non-ordinary case, because what I said earlier has always been about the ordinary case because of this denominator that comes out, right? So if you have this alpha F and alpha G in the denominator, you get something non-integral. So if F and G are non-ordinary at P, then you have to do something slightly different. Then, like, you would get a system of elements still, but they are not integral anymore. They would give you something like this. So right, so we get, so here you actually have 4 sets of elements to consider, because there's no, like, you have let's say F and G are good non-ordinary, maybe should have said that, good non-ordinary at P. Then you have 4 possible sets of elements, because you have alpha F, beta F, alpha G, beta G. So we get 4 sets of elements. Maybe, sorry, I'll write it better. and they're non-integral. So four sets of elements, but it's not so bad. It turns out that you know how big those denominators are, so somehow you can massage them to give you some bounded elements. So by doing some kind of so yeah, maybe I just sorry. I'm not being very precise here. I should start again. So if f and g of good reduction, not necessarily non-ordinary. So let's say they are of good reduction at P, then we get 4 sets of elements. And then it turns out that these four sets of elements give you some non-relation. They are not necessarily bounded, but when, let's say when F is ordinary at P, but G is not ordinary at P, then we can decompose these elements into some bounded elements via some kind of plus and minus techniques inspired by Kobayashi on plus and minus Iwasawa activity. We can get, I'll call this maybe B, F, M, P, N. So I said F is ordinary, so I would say like this. I would write this sharp and flat using the notation of sprung. So using plus minus or sharp flat theory of Kobayashi and sprung. And so once you have some bounded elements, and you can do something similar before, you can you now do have an Euler system, and then you can prove one inclusion of the signed main conjecture. Also here, F can, since F is ordinary at P, then I can deform F in some Hida family. So okay, yeah, maybe I just say this is work by Bujuk and myself. Bujuk. We can also deform F in a CM Hida family. And in this case, we can then get an Euler system. We can actually get a 2-variable Euler system. We get an Euler system for the ZP square extension of an imaginary quadratic field where P splits, and then you can study Iwasawa main conjecture for this P square extension as well. Yeah, so I mean, there are lots of works that can be done using these elements, and then after this, there are lots of recent works for other representations. So I will just briefly mention more works can be done for other representation, like GSP4. There's work on GU21, etc. So so these are works by other people. Skinner, and other people. And so, and these constructions also have quite similar flavor, but as the representations get more complicated, then the constructions become more complicated. So yeah, so I think my time is up. So I'll finish here. Thank you for your attention.
Thank you very much. So are there any questions or comments?
Hello.
Yeah.
So, any hypothesis on the representation of F or E?
The hypothesis is that I want the representation to have good reduction at P.
Okay.
And
Doesn't assume
so,
anything on reducibility or reducibility?
I'm sorry?
Reducibility or reducibility, not P reduction.
Oh, I see. Okay, so in order to prove one inclusion of the Ramanujan conjecture, the Euler system machinery imposes certain condition on the representation. Indeed, so indeed, for the inclusion to hold, I need to make sure that there's big image hypothesis and so on. So I didn't talk about those hypotheses in the when I gave you the statement on how Euler system proved one inclusion of the main conjecture. So I need to make sure all those hypotheses hold, and it includes some irreducibility of the reduced representation as well. So yeah.
So this construction happens for any mod free reduction.
Right. You mean the construction of the Euler system?
Yeah.
Yeah. For the construction of the Euler system, I only need to make sure that P is a good prime.
Okay. Okay. Thanks.
Any other questions?
Maybe this is a stupid question, but this big image thing, how do you see this in the case of cyclotomic units?
Oh, I mean the in the case of cyclotomic units, my representation is dimension 1, right? So like so it is like you know exactly what the
Right,
image
right.
is.
Thank you.
Any other questions or comments? If not, let's thank the speakers for the series of wonderful lectures. Thank you very much.
Thank you for listening.